So we're talking about acids and bases here. And what you should know is that the definition, as you guys have learned, is the Arrhenius and the Lowry-Bronsted. We're going to introduce a new one here, not so much in depth, towards the end of this chapter, called Lewis acids and base. And you probably were exposed to that in your prior course. But acids are chemicals that tend to um, release hydrogen. And so what they will do is when they release hydrogen, they tend to dehydrate or remove water from certain things like carbohydrates. Now, there's a movie here that won't play in my iPad, but you guys can certainly watch it. Basically, the illustration is you pour sulfuric acid in this glass of sugar. And what it'll do is it'll remember sugar is nothing more than carbohydrates. Carbohydrates is carbon of water. So if you look at the structure, you'll see OH groups all over. The hydrogen will go in and remove the hydrates in the carbohydrates, and all you get back is carbon. So that's what acids can do. Here are some properties, of acids and base. Acids tend to taste sour, and you know this from biting into a lemon or tasting lemon. They dehydrate substance. Dehydrate means removing water. They neutralize base, of course, because H plus and OH minus react to form water, and they dissolve metal easily. Okay, examples are tomato juice, orange juice, apple juice, okay, and wine, banana, coffee. Vitamin C is ascorbic acid, and soda has a lot of phosphoric acid as well as citric acid. So those are just example. In this particular movie right here, you put carbon dioxide in water, and the reaction goes to carbonic acid. And you guys may have done this experiment in Chem 152. Okay, carbonic acid is an acid, but it's very unstable. It'll easily break down to, in this particular case, bicarbonate, HCO3 minus, and hydrogen ions. So what happens when you put, and I used to do this when my daughter was young, I would go to her class and I'd be the center dad. Center dad just means that you go in on certain, like Friday afternoon, and demonstrate or talk about science. So that's what I did. Was one of the demonstration was I took some carbon dioxide, dry ice, basically, put it in water. You see the water starts to boil, basically. The carbon dioxide and the water is reacting, and if you put indicator there, it'll change the color of the indicator, going from, say, neutral all the way to acidic. If you put a little bit of base in the water, then you make the water sort of pH like 13 or 12. And then as you put carbon dioxide, you watch the indicator, universal indicator, or cabbage juice is really good. You watch it change color as the pH drops all the way down to about 2 or 3. Okay, so again, it's a reaction that occurs to this day when it rains. The rain comes down from the sky, it reacts with the carbon dioxide in the air, and the rainwater that we receive here at sea level is actually slightly acidic. Base, on the other hand, are chemical that tastes bitter. Okay, it denatures protein. What does that mean? It basically breaks the three-dimensional structure of proteins. That's why you should never handle base directly. An example of a base might be like your drain cleaner, Drano. Okay, what happens in that particular case is that it'll react with the proteins in your finger and then break it down, and so the reaction's really bad. It neutralizes acid, it turns metals to hydroxide. And then examples of base, milk of magnesia, of course, is not a very harsh base, and you use that and take that if you have acid reflux in your tummy. So it neutralizes acids, milk of magnesia does. Lime water also is a base. Lye, Drano. Lye is what it's basically like the way they used to make soap in the old days was they would take the fat from the cows or pigs that they kill, and then they mix it with ash, and then they would stir it up, and then they would make soap from that. So it's sort of basic, okay? Liquid plumber is another base. That's why your drain cleaners are really efficient, because what will happen is that mostly the things that clog your drain is like meat or hair, and base tends to react with it and break it down. Your blood is slightly basic, and as I said, soap is sort of basic. Okay, so these are just examples of common items, and you guys saw this in activity 4B when you did the pH of household chemicals. For those of you in lab, you know which chemicals are acidic and which chemical are basic. So again, it's just to expose you to things that are around us that have those characteristics. This right here is, let me just, again, the demonstration of carbon dioxide and water. And again, it'll change color. You should know this if you have not already covered it in your previous class. Probably some of you covered it in general chemistry when you looked at different reactions. A lot of you covered it in intro chemistry, Chem 152, when you had acid base. But most acids, at least the common ones, have a cation and an anion. The cations are the chemicals that are going to break off. Hydrogen is your cation in acid. And then the anions, what's left off. Together, when you have the cation and anion, you have a neutral substance, okay? But what will happen is that, and remember, we're always talking about aqueous solutions. We're not in organic chemistry, so you're always dealing with aqueous solutions. That means that our solvent's in water. When you put an acid in water, the hydrogen comes off and you have the anion. So recognize these anions that I have right here. The first one's a nitrate, the second one's a nitrite, phosphate, phosphite, ClO4 is perchlorate, ClO3 is chlorate. So again, these are common polyatomic ions, except for iodine and fluoride. Those are halogenated ions, okay? But what happens when you put a hydrogen to these? Well, when you have a hydrogen to these, then you make the acid. Remember, these are all anions, so if you put a hydrogen, which is plus, then it becomes neutral depending on hydrogens you add. So that right there would be nitric acid. That right there would be nitrous acid. That right there, if you put 3 hydrogens, is phosphoric acid, but you can put 2 hydrogens or 1 hydrogen, okay? So if you have 2 hydrogens and a PO4, it's dihydrogen phosphate, but it would not be neutral because phosphate's -3, 2 hydrogens would be +2, so that would make the overall chemical -1. How do you make it neutral? You put a metal. KH2PO4 would be neutral, where you have 3 positive, a potassium, and 2 hydrogens. And that is a salt, okay? Whenever you have a metal and an anion, you have an ionic substance, we call it a salt, okay? And for those of you who are in lab, your unknowns are going to be salts in general, okay? So keep that in mind. Anyway, this chemical right here is phosphoric acid. That right there would be phosphorus acid, phosphorus, because PO3 -3 is phosphite, phosphite. So I hope you guys are remembering these polyatomic ions, because it's important, or at least get yourself a good list of these polyatomic ions. It's important in terms of the language of acid base. And if you're taking the MCAT, best to memorize these polyatomic ions, these common acids, because they're not going to give you a cheat sheet, and it's not going to be an open book MCAT test, okay? So these are the common ones. So here are more, okay? That's perchloric acid. This is chloric acid. This is chlorous acid, and this is hypochlorous chlorous acid. Notice that the polyatomic ion goes from ClO4, ClO3, ClO2, ClO. You guys should remember that series. That's the hydroiodic acid, hydrofluoric acid. In here would be hydrochloric acid, hydrobromic acid. That is carbonic acid, okay? H2CO3, it's common acid that you find in sodas. That's common acid that regulates our blood pH. If you remove one of the hydrogens and put Na to replace the hydrogen, so you have NaHCO3, that would be baking soda. That would be baking soda. Baking soda is sodium bicarbonate. HCO3 is not, it's hydrogen carbonate, but it's more known in common lingo as a bicarbonate, okay, bicarbonate. So H2CO3, that's carbonic acid. If you replace both the hydrogen with, say, sodium, Na2CO3, guess what? You have baking powder. Okay, that's baking powder. If you just replace one of the hydrogens with sodium, then you have, Na2CO3 would be not baking powder, baking soda, okay? And then NaHCO3 would be baking powder. Don't ask me why they name it that way. It's just from old tradition. That's carbonic acid. Hydrocyanic, you don't want to deal with that. That's a poison. It's got cyanide. And this you should recognize, that's acetic acid. That's the common acid in vinegar. And this right here would be dichromic acid. So these are common acid. And you notice this is the nomenclature that you have in terms of going from the oxy ions to the acid name. Like this right here, per 8. Let's take a look at this right here, okay? That chemical, ClO4, is perchlorate. Perchlorate becomes perchloric acid. In other words, you don't have to memorize the hundreds of acids out there. You just have to recognize a lot of the patterns. And then if you understand the patterns, then it's easily named. So just remember that from your fundamentals of chemistry, your intro to chemistry. Here I present it just to remind you. Then these are the definitions. The definitions, the first one is Cervantes Arrhenius. Yes, the same guy that gave us the Arrhenius equation in kinetics. He said that acids were anything that increased hydrogen ion concentration. Hydroxides are anything that increases hydroxide ion concentration, or base, that is, or anything that increases OH minus concentration. Then you have Bronsted and Lowry. And Bronsted and Lowry is not one person, they're two scientists. And that's the general definition that we will be covering in this chapter. It's acids are proton donors, any chemical that will deliver a hydrogen. And then base are any chemicals that will accept the hydrogens. They're proton acceptors. And then the general definition for acid-base chemistry is the Lewis acids and base. And then we don't define acids or base in terms of hydrogen. We define it in terms of electrons. And it's a more universal definition. That's why it's generally more broad. As we go from the Arrhenius to Bronsted, Lowry to Lewis, we extend the family of chemicals that can be called acids and bases. Okay, we extend the family of chemical that can be called acids and bases. Anyway, we will concentrate mostly on these chemicals right here in chapter 16. So the Arrhenius definition, anything that increases hydrogen ion concentration, base, or anything that increases hydroxide ion concentrations. And so you just have to look at the formula in order to recognize whether or not a chemical is an acid or base. If it has a hydrogen, then most likely it'll be an acid. Whether it's going to do it, it's going to give its hydrogen 100% of the time or less than 100% of the time, it's still considered an acid. Base, on the other hand, you're looking for chemicals that has OH on them, okay? But don't look at organic alcohols. Yes, alcohols have OH. OH is the functional group, but that OH in alcohol is strongly bonded to the carbon that it doesn't break. So it doesn't make it a base, okay? Chemicals, hydroxide that are bonded to cation, they want to break up in water because they want to separate into their ions. Now that's going to be a chemical that's a base, okay? So when we talk about acids and base, we talk about chemicals that want to dissociate. What does dissociate means? That wants to break apart. So you get a positive and a negative. The positive in acid will be hydrogen ions. The negative will be the anion. Okay, the anion in most part will be spectators, but in other parts they will actually react in water and change the dynamics. So that's where Chem 201 comes into play. Okay, what will happen is that some chemicals will give you the hydrogen, but then the anion does a little bit of acid-base chemistry. And that's the key. The difference between what you guys probably learned in general chemistry and maybe for the most part in Chem 152 and this course, you have to look at the other things that goes on with the anions. So in order to understand the chemistry by which these things dissociate, again, break apart, you have to remember whether something is an electrolyte, a weak electrolyte, or a non-electrolyte. Remember, electrolytes are chemicals that breaks apart in solution, water generally, and then is capable of conducting electricity. Why can they do that? Because they have charge in solution. Okay, so a strong electrolyte is a chemical that will break apart 100% of the time. A weak electrolyte is one that will break up less than 100% of the time. And then a non-electrolyte is a chemical that doesn't break apart at all. Sugar is a non-electrolyte. It doesn't break apart at all. It stays intact. And so it's not going to give you ions in solution. So it can't support electricity. Here are examples of strong electrolyte. Why is it so important? Because your strong electrolyte, especially when we talk about acid-base chemistry, there's a limited amount. In acid-base chemistry. And if you can remember the strong electrolyte, then for the most part, you can consider all the others that don't fall in this category as weak. In other words, it doesn't dissociate 100% of the time. So here's an example of a strong electrolyte, perchloric acid. Perchloric acid, if you put it in water, breaks up 100% of the time. If you've got 100 moles of HClO4 in water, this will break up to 100 of these and 100 of these. In other words, it breaks up 100% of the time. So it's a reaction in which there is no equilibrium. It only goes in one direction, dissociation. That's by definition what a strong electrolyte does. That's by definition what a strong acid does. On the other hand, and nitric acid is also one of those, okay? On the other hand, if you have a chemical like H2S or nitrous acid, HNO2, that's a chemical that when you put in water, yes, it dissociates to hydrogen, but it doesn't do it at 100% of the time. There's actually an equilibrium involved where these two now can back react and form the reactant. So there's an equilibrium involved, and that's why you need to understand equilibrium in acid-base chemistry. You don't need to understand acid equilibrium when you have a strong acid, a strong electrolyte, but you do need to understand equilibrium when you have weak acids and weak bases, okay? And so the fundamentals that you learn in chapter 15 applies here for weak acids, weak bases, weak electrolytes, okay? So here are examples of base. Here are examples of base. Sodium hydroxide. You put that in water, remember, sodium uh, anions or salts that have group 1 in them dissociates 100% in water. Remember the solubility rule. If they dissociate 100% of water, that means sodium hydroxide will give you 100% hydroxide for every sodium hydroxide that you put in. Sodium hydroxide is a strong base, as well as calcium hydroxide. In this particular case, you got to be careful, because for every 1 mole of calcium hydroxide, you get 2 moles of hydroxide. So if you've got a 1 molar or 1 molar calcium hydroxide solution, 1 mole per liter, then your hydroxide will be 2 molar, because it will give you 2 hydroxide for every 1 calcium. Let me tell you this right now, that this is important, because when you do a titration, okay, you got 1 molar calcium hydroxide and you're titrating it with hydrochloric acid, then your hydrochloric acid would be, you need twice as much hydrogen ion to neutralize that amount of calcium. This is important because those are some questions that I see students miss a lot. There's a question on the chat. The acid in our stomach can conduct, yes, it can conduct electricity. Of course, in fact, the electrolytes in our body, our blood, should be able to conduct electricity. The acid in our stomach is actually pH 1. The acid in our stomach is actually mostly hydrochloric acid, okay? But it doesn't affect us because we have a lot of chemicals in there that neutralizes it, okay? But if it gets too much, if you get acid reflux, you know, you guys know what that feels like. You get a burning sensation in your throat, okay? That's why folks who are bulimic and make themselves throw up, you find out that their esophagus gets worn away because the acid basically breaks it down. It's like having too much acid in pipes. Eventually, the metal will be worn down and then you get leaks. Esophagus, if people are bulimic, they wear down their esophagus and then it ruins their health. So it's not good to do that. We have a lot of acid-based chemistry that happens in our body, and you guys will see that when we start talking about buffers, okay? So again, chemicals that will dissociate 100% of the time, they're going to be strong, whether it be an acid or a base. Sodium hydroxide, lithium hydroxide, potassium hydroxide, those are all strong base, okay? And I'll give you more example. Ammonia is a chemical that doesn't have hydroxide. That's why it doesn't fit into the definition of the Arrhenius base. But ammonia gives us hydroxide indirectly. In fact, you will find out that most chemicals do not give you hydroxide directly. They do it by the reaction with water. You guys know that water is H2O, H, oxygen, H. When you remove the hydrogen in H2O, you get hydroxide. So that's what ammonia does. It removes the hydrogen from water. It becomes from ammonia to ammonium, but what remains is hydroxide. That's where you get your basic solution. And this doesn't happen 100% of the time. That's why ammonia is a weak base, okay? So remember these. Put a star on it because these will be your strong acids. And there's only 7. There's only 7. If you remember these 7, then you can consider everything else weak. Yeah, there are a few exceptions out there that is beyond these 7, but these are the 7 most common strong acids. You put this in water, they dissociate 100%. Okay, and this list goes sulfuric acid, H2CO4. Sulfuric acid is the same acid that you find in your car battery, okay, H2SO4. When you put in water, you get hydrogen and HSO4, the anion. Perchloric acid, HClO3. Chlorous acid, HClO3. I mean, HClO4 and HClO3 are the chloric acid and chlorous acid. This is nitric acid, nitric acid. But nitrous acid, HNO2, is not in that list. Okay, there's not enough oxygen to make that very strong. And then your halogenated acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. Notice HF is not in that list. And the reason why HF is not in that list is because fluorine is very electronegative. It's very electronegative. But it also binds to hydrogen much more strongly than HCl, HBr, and HI. Remember the definition of an acid. An acid is a chemical that easily, willingly gives up its hydrogen. If you've got a strong hydrogen and ion bond, then that's not going to be a very strong acid because that chemical will hold on to its hydrogen and doesn't want to give it up. So that will be a weak acid. HF falls in that category. It's a weak acid. HCl, HI, HBr are strong acid, and you will see why in the later chapters. Okay, what are the characteristics of a chemical that makes it a strong acid or a weak acid? Okay, among weak acids, why are some stronger than others? And you can actually get that through the structure of the chemical. If you write the Lewis structure and you get the geometry, you'll be able to see the reason why some chemicals will easily get rid of their hydrogens, others do not. But under certain conditions, they do give it off. So that makes them a weak acid. So these are the 7 strong acids. These are the 7 strong acids. And outside of this 7, you can consider it weak, which means that you have to deal with the equilibrium. These acids, no equilibrium involved. So don't try and create an ice table for these chemicals. You don't need to. They give you 100% hydrogen. Please remember that. Only strong acids will dissociate 100% in water. The Ka in these chemicals are very, 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 very large. In fact, they're so large, you can treat it as a one-way reaction. Okay. These, again, that's the chemistry. Notice it's a single arrow. It's a single arrow. Don't try and look for Kas for these because they don't exist for a lot of these. Why? Because they're 100%. H2S, you have a double arrow. You have a double arrow, which means that once a product forms, some of the product forms, it can back react. Okay. Here are examples of weak acids. Now, remember what we learned from chapter 15. Chapter 15 is a equilibrium, and we learned about equilibrium constant. And what did we say about equilibrium constant, KEQ? Yeah, we use Ka. Ka tells you it's an equilibrium acid constant for acid. Kb tells you it's an equilibrium constant for base. We're very imaginative that way. Kw tells you it's an equilibrium constant for water. Okay, but here we have the Ka because it's the equilibrium constants for acids. And remember what we said in chapter 15, equilibrium constant tells you about the efficiency, how well the reaction goes to the product. Take a look at this reaction right here. Okay, take a look. I'm going back. This tells you it's an equilibrium. So if that Ka is large, then it's mostly product. If that Ka is small, then some products, mostly reactant. All weak acids will have Ka less than 1. Never negative, but less than 1, which means that the majority of the chemical stays as the reactant. A small amount of it actually gives you hydronium. And that's what you see right here. If you look at this right here, you see that the Ka for iodic acid is 1.6 times 10 to the minus 1. That's less than 1. That's 0.6 0.16. So among this list, this has a better efficiency of giving up its hydrogen than this guy. That Ka is 1 times 10 to the minus 10. Okay, that's 9 zeros before that 1. It's not very efficient in giving up its hydrogen, but it does give up its hydrogen eventually because we're dealing with moles and moles and moles of chemicals. So you can monitor the amount of hydrogen that is in that solution, albeit it's very, very low. So among weak acids here, okay, this is the strongest weak acid. We abbreviated WA. This is the weakest weak acid. Just look at the Ka, okay? Later on, you guys already know that if you have hydronium ion concentration, you can calculate the pH. Okay, you learned that in 152. You basically take the negative log of the hydronium ion concentration, and that'll get you the pH. We can do that with Kas, okay? Why do we do it with Kas? Because these exponents are very frustrating. These exponents are very frustrating. If we take the negative log of the Ka, we actually get the pKa, okay? And sometimes the acids are quoted based on their pKa. They're quoted based on your pKa. The bigger the pKa, the weaker the acid. Just like the higher the pH, the weaker the acid. If you have a solution that has a pH of 5 versus a solution that has a pH of 2, the pH of 2 will be more acidic than the solution that has a pH of 5. Likewise with pKa. If you have pKa of 1 versus a pKa of 7, the pKa of 1 is going to be a stronger acid because that has a Ka of 1 times 10 to the minus 1. pKa of 7 means that your Ka is 1 times 10 to the minus 7. Very small in terms of going into the product, okay? So just a heads up, because a lot of the fundamentals you already learned from Chem 152, you're going to expand that knowledge here in 201, okay? So let's take a look at base. In bases, you don't have a list of 7, but you do need to remember the solubility rules. And in the solubility rules, the most important part is the cation, because remember, hydroxide is the anion. So if you know the cation and the solubility of the cation, then you'll be able to figure out which are strong bases. Because if you know that the chemical, the salt, bases are salt, okay? Because it's got a cation and anion. But if you know that that thing will, when you put it in water, dissociates 100%, then you know that that thing will give you 100% hydroxide. And so I remind you about the solubility rules. Group 1, alkali metal salts, sodium, potassium, rubidium, okay, cesium, lithium, hydroxides are going to be strong bases. Group 1. Heavy group 2, anything below calcium, strontium, okay, barium. Heavy group 2, hydroxides are going to be very soluble in water, which means that they are also strong base. Strong base, heavy group 2. Heavy, when we say heavy, we mean the molar mass of the metal. That's what we mean by heavy group 2, okay? Yeah, I know some of the descriptions that we have in describing these things, they come from the old days when chemists just kind of like knew what these things were. And so we're expecting you guys to know that heavy group 2, calcium, and higher in terms of alkaline metals. And then you also have oxides. So if you got an oxide that easily dissolves in water, what are oxide? Na2O, Li2O, CaO. These are all oxides. You get it and you dissolve it in water, what will happen is that these guys will break apart, and then the oxygen will break the water and tie one of the hydrogens in water, and you get OH. So for every one oxide, you get 2 OH, because not only do you get the OH from water, you also form the OH when that oxygen attacks the hydrogen in water. So in oxides, the hydroxide that you get is through the water chemistry. That's why you need to understand a little bit about water chemistry, because it plays a big role in acid-base chemistry. Anyway, these are all strong base. You put it in water, they dissociate 100%. Heavy group 2, they're all strong base. But please remember that for every 1 mole of this, you get 2 moles of hydroxide. And this is important once we get to titration, because it's not a one-to-one reaction. It goes back to stoichiometry. For every 1 mole of these calcium hydroxide, you need 2 moles of hydrogen ion to neutralize it, because it's a 1-to-2 ratio. Okay. Then there's these are your oxides. And your oxides, when you put it in water, like I said, the oxide will react with the hydrogen in water. You get 1 OH group, and then the remaining OH from water is your other hydroxide. So this is, again, a 1-to-2 ratio. And these things will dissociate 100%. So again, they're strong electrolyte. Remember, electrolyte's just the definition of whether these things will break apart. It doesn't say anything as to whether they're acids or base. Now, if it's got a hydrogen, that strong electrolyte is an acid. If it's got a hydroxide, then that strong electrolyte is a base. Or in this particular case, the strong electrolyte is an oxide, but it reacts with water to give you the hydroxide. Okay, so there is no list, but you can create yourself a list if you want. Any group 1 hydroxide, any heavy group 2 hydroxide, and any group 1 and heavy group 2 oxides will give you strong bases. Okay, so you can create yourself a list if you want to do that. Everything else will be weak. Everything else will be weak. Okay, here's the chemistry, and let me just show this in a movie, because it's somewhat important.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong electrolyte. Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it is not completely ionized. It is therefore termed a weak electrolyte or weak acid. Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base. It is also, of course, a strong electrolyte. Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the ammonium and hydroxide ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left. At any given time, most of the ammonia is in a non-ionized form.
So here you can see that a strong acid will give you 100% hydrogen ions and the anion. A weak acid stays mostly intact and gives you only a small percentage of hydrogen ion and the anion. So this is a good visual of the difference between strong acids and weak acids. And again, acids are the chemicals that give up hydrogen. And so acids, let's go to the other definition, are called proton donors. That hydrogen that comes off, okay, remember hydrogen has one proton in the center, one electron. What happens is that when this electron is removed, because it gets transferred to the anion, that's why the anion is negative. What you basically have on hydrogen is just a proton. Protons are not stable. Protons actually do not exist in your solution. That proton will actually try and stabilize itself. And if you have a proton, what's the one chemical that is abundant, that can stabilize it? It's actually water. Okay. And so what you have is this hydrogen will react with the lone pairs of water to be stable in that form, and you get H3O plus. Okay, H3O plus. And H3O plus is called hydronium ion. So in acid-base chemistry, a lot of times we say, yeah, it's a proton donor, H plus. In reality, because of the AQ subsymbol there, it's actually the hydronium. So we use it interchangeably. And then the hydronium actually gets stabilized by the water molecule around it through Coulombic interaction. Hydronium is polar, water is polar, and it stabilizes that way. When you have this complex type of chemical, then what you could have is H3O plus or H5O2 plus or H7O3 plus. Okay, but the main thing there is that this actually has two waters and an H3O plus. And the one water, sorry, it has one water and H3O plus. That's how we get H5O2 plus. The water stabilizing the hydronium. Okay, that's the hydration process. Remember, water is polar, so it can orientate itself and stabilize either a negative charge or a positive charge. So you can do it in this fashion, H5O2 plus, or this fashion, H7O3 plus. Again, it's the hydration process that stabilized that hydronium ion. But you guys don't see that. All you do when you deal with chemistry problem is deal with the hydronium ion, H3O plus. Okay, but that's what happens in the solution. A lot of things goes into solution. Sometimes we ignore it so that we can simplify the picture. Okay, so again, H plus in reality is H3O plus the hydronium. We interchange these terms. So the question really comes to mind as to why does water have a pH of 7? Okay, pure water at 25. It has to be pure water, can't be contaminated, and it has to be at 25 degrees Celsius or 20 degrees Celsius. Okay, 20 degrees Celsius. Why is that a pH of 7? And you're going to say that it's because it's neutral. That's the wrong answer. Okay, that's the wrong answer. Don't ever tell me that it's neutral, because at a different temperature, pH 7 is not neutral. The main reason it's pH 7 at 20 degrees is because both the hydronium ion concentration is equal to the hydroxide ion concentration at that temperature. That's why it's neutrality is when the H plus and the OH minus are equal to each other. The pH equals to 7 is because of the Kw of water. And you'll see that in this discussion. Okay. So water is what we call amphoteric. Amphoteric means that a chemical can behave both as an acid and a base. In one situation, it can be a proton donor. In another situation, it can be a proton acceptor. Okay. Proton donor, the hydrogen will give you a hydrogen ion and then a whole hydroxide remains behind. Proton acceptor, it takes a hydrogen and then what happens is that you get H3O plus. So this reaction in which water becomes both a proton donor and a proton acceptor happens in 2 in 1 billion. 2 in 1 billion water molecules will do this, what we call self-ionization. And the self-ionization, where the hydrogen goes to the lone pair of another water, okay? Or in this particular case, let me make this clear. This hydrogen right here goes to that lone pair right down here. And what you get is that this chemical, this water, is the proton acceptor. So in this direction, it's the base. This chemical is the proton donor. So in this reaction, it's the acid. But it gives you H3O plus and OH minus. That's called the autoionization of water. And it happens only in 2 in 1 billion. Okay, 1 times 10 to the 9th. If it only happens to 2 molecules in 1 times 10 to the 9th, what do you expect the Kw for water to be? Very, very large, or equal to 1 approximately, or very, very small? Well, 2 in 1 billion is a very small amount. So you're going to expect the Kw for water to be very, very small. And you guys have seen this. The Kw for water is 1 times 10 to the minus 14 at 20 degrees. At 20 degrees. It changes when you change the temperature. Equilibrium constants is a function of temperature. We saw that in chapter 15. You change the temperature, you change the equilibrium constant. At 20 degrees, it's approximately 1 times 10 minus 14. It's actually 1.01 times 10 to the minus 14. Anyway, because it's very rare, the amount of hydronium and hydroxide in pure water is also going to be very small. Remember, the fact that the reaction goes to the right means that the products do exist, albeit in a very small amount. And so we have this, we have this right here. It's an endothermic reaction. Delta H for this reaction is 55.9 kilojoules, okay? The K equilibrium is called KW, and for 25, I say 25 degrees, but 25, 20 degrees, sometimes I forget, but around that temperature, 20, 25 degrees, the KW is 1 times 10 minus 14. In fact, here it is right here. I got that wrong. See, sometimes I don't remember these things. At 20 degrees, it's 0.68. At 25, it's 1.01. So remember, 25 degrees. I should remember that. Okay. The reason why 20 degrees is stuck in my head is because the density of water at 20 degrees is 1. Okay. So that's why I forget. But the KW at 25 degrees is 1.01 times 10 to the minus 14. This is a list. It shows you that the KW, the equilibrium constant for water, changes at the different temperature. Now you might ask yourself, well, why is it pH 7 at 25 degrees? And it goes back to the equilibrium. Remember, this is a weak acid, albeit it's an amphoteric chemical. It still gives you hydronium. So it's a weak acid as well as a weak base, and we can do an analysis on it. So we can do this right here. Before we do that, remember there's a balance between hydronium ion and hydroxide ion. When your solution contains more hydronium ion than hydroxide, it's acidic. When it contains more hydroxide ion than hydronium, it's basic. When they have equal amount, that's neutral. pH 7 does not mean neutral. Neutral tells you that the hydronium and the hydroxide are equal. So that's what you see in this slide. Acidic when hydronium is greater than hydroxide. Neutral means those two are equal. Basic, hydroxide is greater than hydronium. And there's a relationship there that you will see based on what we're going to be talking about next. So how does Kw dictate the hydronium and hydroxide concentration? Look at this right here. When water dissociates, H2O plus H2O, and these are liquid, goes to hydronium, and that's aqueous because it's stabilized by water, and hydroxide. And that's aqueous because it's stabilized by water. But the mass action expression for that is hydronium times hydroxide equals, remember, you're not going to put anything in the denominator. Why? Because these are liquid. Nothing goes in the denominator. Liquid has a constant concentration. Equals K equilibrium equals KW. But at these two happen at the same concentration. When water reacts with another water, you form equal amount of hydronium and hydroxide. If you don't put any other chemicals in there, you just let water sit alone. 2 in 1 billion, 2 in 1 billion now, we'll do this. So we can say that this KW is just equal to X squared, where X is equal to both the hydronium ion concentration and the hydroxide ion concentration. And we know that Kw is 1 times 10 to the minus 14. If you do the math, you take the square root of both sides, you find out that X equals 1 times 10 to the minus 7 molar. This is only when Kw equals 1 times 10 to the minus 14. If Kw was 1 times 10 to the minus 16, then guess what? X, or hydronium, would be 1 times 10 to the minus 8. Okay? So please keep that in mind, because that's exactly what you see right here. Okay? When we deal with the mass action expression. Why are we dealing with the mass action expression again? Because this is an equilibrium. When we have an equilibrium, we have to deal with the mass action expression. When we don't have an equilibrium, then you treat it stoichiometrically. Stoichiometrically just means that everything turns to product 100% of the time. So you can see right here, this is exactly what I wrote over here. You guys can follow that. And then before we move on, 1 times 10 to the minus 7 molar, very intimidating to the general public. The general public hate exponent. They don't understand exponent. Unlike you guys who are science students, you guys deal with exponent, big numbers, small numbers all the time. So we need to please the general public. How do we make this number not so intimidating? How you make a number like 1.56 times 10 to the minus 4 less intimidating? Well, we do that by something called the P function. The P function, power of hydrogen. And you guys have seen this in your previous chemistry class, where if you take an exponent and you take the log of that number, then you get a number that's not so exponential. So if we take 1 times 10 to the minus 7 and we take the negative log of 1 times 10 to the minus 7, our calculator will spit out 7.0. Okay, so that's the P function, the power of hydrogen function. Now we know why water has a pH of 7. The P is because we convert 1 times 10 to the minus 7 to a log function. Okay, we take the log of that number, and that's the number we get out. But more importantly, the pH of water is 7 at 25 degrees because Kw is 1 times 10 to the minus 14. If Kw was any other number than 1 times 10 to the minus 14, we would get a different pH at neutrality. At neutrality, when hydronium and equals hydroxide, because what does the hydronium concentration measure? It measures the amount that is in the solution. So this is the P function. Make sure you guys review that, because you guys are going to be doing that a lot in this particular section. Okay, and again, I just show you how you would punch this in your calculator. Okay, I don't have time to kind of like go through your calculator concentration. I did that, I think, in 152 and in my chemistry 100. If you have problems figuring it out in your calculator, please email me and we can walk through it. But you guys should know how to do that in your calculator. Okay. The two functions that you guys are going to do is the log and 10 to the x. The anti-log function, this is the anti-log function when you do a calculation, 10 to the x. Anyway, you can see that in our P scale, that concentration, 0.000001 is 1 times 10 to the minus 7. When you do the P function, you get a pH of 7. This is also equal to the hydroxide ion concentration. If you take the negative log of the hydroxide concentration, you get POH, that's 7. So that's neutral because they're the same at 25 degrees, I always got to tell you it's at 25 degrees because if it's not 25 degrees, then those numbers change depending on the kW. This right here is acidic, and you can see that the pH 1 times 10 to the 0 is just 0. On the other hand, you know that hydronium ion concentration times hydroxide ion concentration is equal to kW 1 times 10 to the minus 14. And so if the hydronium is 1, then the hydroxide is 1 times 10 to the minus 14. And if you take the negative log of 1 times 10 to the minus 14, you get a POH of 14. So small pH means it's acidic, means you got a high amount of hydronium. Low pH means that your hydronium, your hydroxide is high. Okay, your hydroxide. Here, your hydroxide ion concentration equals 1 molar because your hydronium H3O plus concentration is 1 times 10 to the minus 14. So there's always a balance. There's always a balance. If you're looking at just pH and POH, they all add up to 14 at 25 degrees because your pKW equals 14 at that temperature. If your pKW was 16 instead, then they should add up to 16. Okay. And so that's basically the P function that you see right here. We can do a P function for any number that's in the exponent. We have something called the pKW, we have something called the pKa and the pKb. It's just taking the negative log of that value. Okay, it's just taking the negative log of that value. This is something that I do for my beginning student, but you guys could find this useful as well. Given any one of these, hydronium, hydroxide, pH, or POH, you can calculate the other three. The only other thing that you need is either the KW or the pKW. Why? Because you need to know how the hydronium and the hydroxide relate to in that particular situation. Remember that the hydronium times the hydroxide, and this is the mass action for water, equals kW. So if you know kW and any one of these, then you can calculate the other. And then if you have the other, then you can calculate its P value, its power value, and you can certainly calculate the rest of these. So hydronium and hydroxide, they're related by hydronium times hydroxide equals kW. So if you've got the hydroxide, then take your kW and divide it by hydroxide. If you got your hydronium, take your kW and divide it by hydronium. These right there, this is probably the most easiest equation in this whole thing. pH plus POH, just like you saw in that previous slide, equals 14. As long as kW equals 1 times 10 to the minus 14, as long as pKW equals 1 times 10 to the minus, pKW equals 14. If it's something else, then that right there needs to be that something else. Okay, so you guys can do that. And then this is the log function. This is the power function, P, whatever that is, negative log of the hydronium gives you the P value. And then the anti-log is 10 to the minus pH will give you the hydronium. Going in reverse, this is the anti-log. So practice with your calculator, not so much when we get into acid-base chemistry. Likewise here. Okay, so this is a really useful slide to show you that relationship. Given any one, this or this or this or this, you don't need two or of these, you just need one, and the KW, you can calculate the other three. Okay, given any two of these, or this and this, you can calculate the KW. Okay, so anyway, these right here are just examples. I'm not going to go through them because I see I'm running out of time. Make sure you review them to remind you of how to do those calculations. This is similar to experiment number 4, part B, where you have the pH of common household chemical. Notice that your saliva is slightly acidic, but your blood is basic. Okay. Again, common household items. And then this is the last thing I will talk about before signing off for today. And then next time we'll look at the real chemistry of acid base. Hopefully, I know this went a little bit fast. Still took an hour to go over, but hopefully you guys were reminded of some of the fundamentals that you guys already covered for your requirement to take general chemistry. But like I said, rainwater coming from the sky is not pure pH 7, even if the temperature outside was 25 degrees Celsius. Okay, and the reason why rainwater is not pH 7 is because as it falls from the sky, it actually reacts with the carbon dioxide, because carbon dioxide's out there. It's increasing more today than it was a few years ago. That's why we have global warming, but it reacts with the water coming from the sky, and it makes carbonic acid. And when you have carbonic acid in water, you get hydrogen ion and bicarbonate. That's what makes the rainwater acidic. Okay, it's never pH 7. So if someone claims that we got to do something for the environment so that our rainwater's pH 7 or neutral, tell them that they don't know their chemistry. Okay, it's always going to be acidic because carbon dioxide. As long as you've got carbon dioxide out there, it's going to be acidic. But we also have issues with pollution. Sulfur dioxide is an gas emission chemical when you burn coal. That's why we're swaying away from coal these days, because when you burn coal and you don't remove the sulfur, that's why it's coal. The clean coal is going to be more expensive than ones that are just mined, because you remove the sulfur. Why do you need to remove the sulfur? Because when sulfur is burned with coal, you not only get carbon dioxide, which is bad, but it's not poisonous unless, of course, you get suffocated by it. But SO2 will react with oxygen in the air and form SO3. And in fact, this happens a lot in eastern mining towns where they burn a lot of coal. And so what would happen is this gas is prominent. And when that gas is prominent, what happens is that when it rains, the SO3 in the water reacts to form battery acid. So for those towns that were mining towns that were burning coal that had sulfur in it, when it rained, sulfuric acid was hitting their head. Not good. Of course, here in the West Coast, we don't have to worry about coal burning power plants. We've sort of eliminated that, but we do have cars. And when cars combust gasoline, it sucks in air. Air is mostly nitrogen. Nitrogen and oxygen gives you NO2. That's the brown smoke that comes from your exhaust. That's why we have these catalytic converters to remove that. But if there's any NO2 out there, guess what? The NO2 will react with water and you get nitric acid coming down your head. So whenever you look in the sky and you see brown haze, that's nitrogen dioxide. Run away when it rains because you got acid coming down. In fact, it was so bad in the 60s, 70s, part of the 80s, before we were more attuned to the environmental effects, that here's my friend George in the Washington Square. This was in 1944. This is what happened to George in 1994. He has leprosy because of the acid rain. Statues, marble statues, is nothing more than calcium carbonate. You take calcium carbonate like chalk. Chalk is calcium carbonate. You put a little bit of vinegar, it eats it away. That's what's going on. When you have acid rain, that's what happens. Okay. In fact, what can happen is you can kill whole forests because of acid rain. So it's not a good. Okay. So I'll kind of stop there just because it's 6:10 right now. The last of these slides just tells you about indicator and how indicator changes the chemistry. The chemical itself changes its configuration under certain acidic and basic conditions, and that's why it changes color. And you guys will see that in your lab today. We will talk about titration today, okay? But for the most part, I hope that reviewing this first section in chapter 16 sort of jarred your memory in terms of certain fundamentals of acid base. When we go into the next section, you'll see how equilibrium plays a big role for weak acids. Okay, weak acids, weak base. But that's all I really wanted to say for that. We pretty much finished this particular section.